Hi, my name is Bruce Linquist. I'm the UC Cooperative Extension Rice Specialist with the Department of Plant Sciences based here at UC Davis. In this presentation, I'm going to be going over managing water in rice systems under limited water conditions. And the basic outline of my talk is first we're going to look at water use and losses in rice systems, rather a broad perspective. But then importantly, we're going to look at some opportunities where we can reduce water use, improve our water use efficiency, but also to discuss practices that might sound like they reduce water, but at least in our systems that we're familiar with here in California, they probably do not reduce water. So with that, if we first look at a cross-section of a rice field, we have here the soil, the water, and the plants. We can look at a number of different losses. Particularly, we look at evaporation, which is the surface, the water loss from a body of water. Transpiration is water loss through the plant. And we combine those and call those evapotranspiration, or ET for short. Other sources of losses are seepage, which is sort of your lateral flow from the sides of the field. We also have percolation, which is downward water movement in the soil. And then we have drainage off the field, tailwater drainage. This can occur throughout the season or under conditions where we want to purposefully drain. If we look at a water balance and just try to get an idea of how much water is used in each of these losses, we have about a little over 7.5 feet total water inputs. And this is based on 6 studies that we've done across California in major rice producing areas in combination with Rick Snyder here on campus. And it shows quite a bit of variability on the amount of water that is actually delivered to a field. But if we break that down a bit and we look at net water use, and this includes ET, evapotranspiration, percolation, and seepage. So these are sort of your in-field losses. It does not include any tailwater losses or any drainage losses. The amount of water that's used for that is much narrower, and we're looking at about 3 to 4.3 feet of water. Further breaking that down to where with these infield losses, we have about 3 feet losses in ET. Percolation, we've estimated to be less than 0.3 feet, and seepage between 0 and a foot. And again, percolation and seepage losses can be highly variable. These numbers are from this particular study. But they would vary, they could vary tremendously in different soils, particularly as you move towards sandy soils or soils without a plow layer where your percolation losses may be quite a bit higher. But percolation on our heavy clay soils is generally small. So if we put those numbers back in our cross section here, we see again our ET losses of 3 feet, seepage losses about 0 to 1 foot, and percolation losses at less than 0.3 feet. In our study, tailwater drain losses were quite broad, ranged from 1 to 4 feet. So certainly a lot of variability and a lot of opportunities to reduce water inputs by trimming the amount of tailwater drains that we have. So what are some possible options that are often discussed to reduce irrigation inputs? And we're going to discuss these each in turn. The first is going to be looking at drill seeding instead of wet seeding. Then we're going to look at allowing the field to dry before reflooding. We'll discuss that a little bit more. There are opportunities to shorten the irrigation period, and this can be done through planting time or the use of short duration varieties. And then we're going to talk about holding the water or going to a no spill type of practice. So if we first look at dry versus wet seeding, the common practice here in California is wet seeding or water seeding. And water seeding is where we fly on seed onto a flooded field, and the field remains permanently flooded from then on out. In dry seeding or drill seeding, what we often see is the rice is planted similar to a wheat or corn crop with a drill seeder. And then we have a couple of flushes to emerge, so that germinate and emerge the crop. And usually after about a month, we go to a permanent flood and the water is held similar to the water seeded system. In dry seeding, we often find that 2 or 3 flushes are required early on to get good stand establishment and even stand establishment. And this can cause some problems. We use up a lot of water is required to completely fill these fields, and then all that water is subsequently drained off that field. During these flushes, you can also get a lot of soil cracking, and so you get downward movement of percolation into the soil, so you get some additional losses there. What we've found because of this is that we've measured no difference in either ET or water use between dry and water seeding in systems. And another reason for this is that dry seeding also delays crop development by about a week, and so you have a longer irrigation period. This is really quite different than in the southern U.S., and the main difference between California and the southern U.S. is that during this crop establishment period, in the southern U.S., they don't use irrigation water to germinate and establish the crop. This is all done by rainfall, so they can see some significant savings simply based on the ability to limit irrigation water during that first month. If we look at allowing the fields to dry between flooding events, and this is really a practice that is used in parts of Asia. It's not used here in the U.S. that much, but it's filling the field to maybe 6 inches and then letting it subside slowly. There's no spill, but it would subside due to ET, percolation, and seepage. And then once the soil dries out to some critical level, usually below saturation, that the field is re-flooded. And you would progress through the season with these alternate flooding and drying events. And these systems, you may have heard of them before. They're alternate wetting and drying or intermittent wetting and drying. They're referred to in those ways. Water savings are possible with this, and we see water savings particularly in soils where there's high percolation and where you can capture and use rainfall. Now in California, our soils do not have high percolation. They're incredibly, have very low percolation. We have very heavy clay soils and a hard pan underneath these soils, which really prevent a lot of downward percolation, which is good for rice systems. And also, we do not have rainfall during the growing season, or at least very little. And so our systems aren't designed to capture and use that rainfall in any way that would help us reduce our irrigation inputs. So the other problems associated with this is there can be high risk of yield loss. We've seen in studies where the soil is allowed to go much below saturation, we see significant yield losses at times. And secondly, our irrigation systems really do not allow for that. In California, we have these cascading irrigation systems where water starts at the top end of the field and moves down through the field. It can take a long time to irrigate a field, and it gets longer as you get into the season as the plants themselves actually restrict the movement of water in that field. And the length of time that it takes to reflood some of these fields, during that period the soils are drying further and further out, and you're likely going to experience some sort of yield loss due to that. Again, this is different than in the South. In the South, they do use some of these systems. Farmers are experimenting with them, but there they have side inlet systems, or they use poly pipe, and there it allows growers to irrigate each of the checks separately and fill them up as needed. So it takes a lot less time to uniformly fill that field. So again, we don't really recommend this practice for use here in California. However, there are some things that we can do, and I'm going to spend the rest of my time really talking about these things. And first is opportunities to shorten the irrigation period. By shortening the irrigation period, we have opportunities to reduce ET. We also have, as long as that field's flooded, you do have percolation and seepage losses. So by shortening it, we're able to reduce all of those. A couple that I'm going to talk about is the effect of planting time and looking at varietal choice. In some studies that we've done, we just asked the question, what happens if I plant on May 1st versus June 1st? These are really the, May 1st represents a relatively early planting date. June 1st for here in California represents a late planting date. And we looked at this on M202, again an older variety, but the principle still holds. And what we found was, if you look at these red bars here, by planting on June 1st, we were able to shorten the crop duration to heading by about 6 days. And so if we estimate how much ET was saved by that, looking at the historical records, we were able to save almost an inch of water by planting late rather than early, simply because we're shortening the duration that the crop needs to be irrigated by later planting dates. We're certainly not advocating planting on June 1st, but we are advocating avoiding very early planting dates if possible. In the past, when we've had very dry springs, it's not uncommon to see growers trying to plant very early, even mid-April. And based on this data, those sorts of practices, those very early dates, planting dates, will result in higher water use. So we suggest, if you have the option, to plant a little later rather than early. If we look at varietal, the choice of variety on ET and irrigation requirements, we see something very similar. Again, if you can grow shorter duration varieties, we're able to irrigate for a shorter period of time. And here we have the example of M202, which has really been replaced in much of California by M206, which is the dominant variety grown here in California. For M206, it requires 4 to 8 days less time to reach heading. Again, looking at the same sorts of assumptions that we used in the previous slide, we're able to save about an inch of water simply by planting a short duration variety such as M206 versus M202. However, time to heading is really not the important period. We really are concerned with the time required for the whole crop irrigation period, and this is really time to R7. R7 is a staging that is where one grain on the panicle has turned yellow. This is a staging system used in the southern U.S. and that we've started to use a little bit here to help us a little bit in understanding how crops develop and to be able to quantify developmental rates. But what we find, recommendations from some of our advisors like Cass have said we really want to be draining our fields about 3 weeks after heading, and this corresponds very closely to R7. And so what we've done is we've had over the past few years a number of experiments where we're actually monitoring varietal developmental progression throughout the states in 6 or 7 trials in each year. And what I've done here on this table is simply put the days from planting to R7 for each of these varieties. These are all the main varieties grown here in California, perhaps with the exception of M105, which is not included in this study. But what we find, and I've grouped them by color, these ones in green, M104, a fairly common variety, CM101, S102, again, relatively common. all of them require 100 days to reach R7. M206 requires about 4 more days. And then if you get to some of these other ones, M202, M205, they require even more. Relative to M104, a week to almost 2 weeks longer to reach R7. And then M401 requires 28 more days, four more weeks simply required for irrigating that crop. So choosing a variety that's short requires less irrigation. We would certainly recommend in a year where we're facing water restrictions, M401 would certainly use more irrigation water, and we would suggest going to M206 or M104 for some of your common medium grain varieties to reduce water use. And finally, I'd like to talk about holding water or no spill. And what this does is it gives us the opportunity to cut our water usage significantly simply because we're not letting the water flow through our fields, but we're holding the water in the field. Our inputs are designed, our irrigation inputs are designed to match the amount of water losses we're experiencing in evapotranspiration, percolation, and seepage. So based on the studies that we've done, we would be able to save 1 to 4 feet of water doing this. It does not change the ET, but certainly we see significant savings, especially on the low permeability soils that we have, because we're not losing much via percolation. So having standing water on the field is not as big a concern as if we had very permeable soils. And so with this, we can limit our water use to 3 to 4.3 acre feet. Again, we'll talk a little bit more about that in an upcoming slide about how we can shift that down from 4.3 to 3. But just to address some other concerns, this is a practice that is done in many parts of the world, including the southern U.S., where no water is spilled from the field. There are concerns here in California, particularly related to salinity. I do know growers that practice no hole or no spill practices, and they have not had problems with salinity, so there are places where I know it can work. Certainly along the west side of the valley where soil salinity is an issue, no spill may be difficult in that, because certainly holding the water will sort of exacerbate, make those problems more difficult and may affect yields. The other issue is that it is harder to manage your irrigation. You have to constantly be monitoring to make sure that your inputs, your water irrigation is matching what you're losing, so you can hold the water at the right level. Related to this is not draining at the end of the season. And this is part of that whole no spill practice. And often the recommendation is to drain the field roughly 21 to 24 days after heading. And what you might be doing at that stage is you might have 6 inches of water in your field at that time, and then you're just going to drain it. That water shouldn't have to be drained, but really what we'd like to see is that you're turning off the irrigation water earlier and letting the water slowly subside, so that when you're reaching that 21 to 24 day period, at that time the soil, the water has drained sufficiently from the field. So when do you turn off your irrigation so that by 24 days it has subsided? Well, it's going to depend on a number of factors, but it's going to first of all depend on the amount of water you have in the field. So if you have a lot of water in the field, it's going to take a lot longer to subside than if you just had a couple inches of water in your field. It's also going to depend on soil permeability, seepage, and climate. If you have a lot of hot, windy days during that period, evapotranspiration will increase and will likely the water will subside faster. So, kind of wrapping up, some suggestions for maximizing water use. In these last couple slides, we're going to kind of summarize some of the things we've talked about and put it in a different sort of framework. First of all, we want to avoid early plantings. Again, this shortens our time that we need to irrigate the crop. Secondly, let's use early maturing varieties. Again, we're shortening the time required to irrigate. So by doing all of that, by avoiding early plantings and using late maturing varieties, it saves on ET losses, but also percolation and seepage losses as well, because the field isn't flooded for such a long period. If you're in a position where you have to plant less acreage, you're only given a certain amount of water and it's not enough for all your fields, you have to make decisions about what fields you're going to plant and which fields you're going to let fallow. We would suggest do not plant on permeable soils. Again, you're going to get a lot more percolation losses. You're going to use more water in those fields. And don't plant on saline soils. Again, if you're going to a no-spill type of practice, probably on your saline soils, there's going to be a higher risk for yield losses due to salinity buildups within that field, because you don't have the water replenishing and flushing out some of the high saline water. Again, we practice no spill. And again, at the end of the season, try to let the water subside rather than draining all the water off at the end of the season. So plan on having the soil drained by 24 days after heading. So in summary, conclusion, rice can be grown here in California with 3 to 4.3 feet. Growing rice with 4.3 feet is possible with no spill management on many soils that we have here in California. The question is, can we reduce that from 4.3 and grow it with less? To do that, again, we can't be letting that water spill at the end of the season. If you have 6 inches of water there standing at the end of the season that you need to drain, that's 10 to 15% of your total water use that whole season just draining off the field. That could have been used during the season. It also depends on field characteristics, as we've described, percolation and seepage characteristics of that field, varietal choice, and your time of planting. And with that, I'd like to thank you.